see, zones, okay. Growth of bone, interstitial growth occurs in the epiphyseal plate, and appositional growth occurs in the periosteum. So that's going to be very, very similar to the way that that happened with the cartilage as well. So appositional growth specifically means that, you know, an infant is going to have that diaphysis be a certain diameter. By the time you become an adult, it's going to have to be a much wider diameter. And by the time you're an adult, the medulla is going to be considerably larger than your infant bone color ever was, right? Which means that as we grow, we actually have to essentially dissolve that bone from the inside and grow appositionally and add to the outside over the course of a lifetime. So that's one of the reasons we were talking about you're going to get those interstitial lamellae. They're going to be the remnants of growth over the span of a lifetime. You had osteons, and then you dissolved them, and then you developed new osteons, and then you dissolved them, and then you developed new osteons, and then you dissolved them. And even in the adults, you're still undergoing constant remodeling. You're still dissolving some calcium every day to utilize it for other tasks, and you're still depositing more calcium. And that's going to happen in response to stresses on your bone. If you are not, and by stress I mean physically utilizing it. It doesn't necessarily mean a bad thing that you stress your bones. A stress to your bones would be like weightlifting, for example. Weight-bearing exercise is going to encourage deposition of calcium into bone. Whereas if you're sedentary and you are not stressing your bones, that's going to encourage leaching of calcium from your bones. They're going to be broken down more. And again, here's that appositional growth occurring as we develop along the appositional surface, along the outside, the superficial growth. We'll also have to develop new blood cells. We'll have to engulf them into new osteons to create those central canals, those circumferential lamellae. That's all going to be a growth and remodeling process. For each long bone, you're going to have some foramen along, and again, a foramen is a hole. You're going to have some kind of hole along the diaphysis. It's going to be your nutrient foramen for your nutrient artery. Now, I think on our short list, we don't have any nutrient foramina. Foramina is plural for foramen. I don't think you have any on your list. Just be aware that they exist. They're often not found very well represented on plastic bone specimens. I've underlined these. These are the ones I physically underlined them, which probably means that they're a jazz hands topic. So a metaphyseal artery, an epiphyseal artery, and paraosteal arteries, along with the nutrient artery. You probably want to know that blood supply pattern. And again, once you know the parts of the bone that you have a diaphysis, and that's going to be called the nutrient artery, that you have a metaphysis, that you have an epiphysis, those are all going to need blood supply. This is a very, very, very vascular organ. Which means if you fracture part of this, that's going to develop a hematoma, a bruise, an accumulation of blood, very, very quickly. Any questions about that? And I mentioned before, you're always going to have nerves, arteries, and veins traveling together. So you will also have nerves accompanying those blood vessels through the nutrient foramen. So you will have highly innervated bone as well. Okay, bone homeostasis. We've been hinting at this all along. All I'm going to expand on now is the hormones that influence it and the vitamins that influence it. So you have cells that deposit bones, osteoblasts, and you have bones. There's cells that deposit bones, and then there's cells that break down bone. The cells that form bone are osteoblasts, the cells that break it down are osteoclasts, and they are influenced by hormones. They do not act independently. You have hormonal signals that stimulate them or inhibit them. So the main ones that I want you to focus on are parathyroid hormone and calcitonin. Those are the two most important on this list for bone homeostasis. They will be influenced by other substances. Growth hormone, not surprisingly, is a hormone that affects growth. Thyroid hormone is a hormone that affects metabolism. Estrogen and testosterone, men and women will experience bone growth, development, and aging differently based on sex hormones. Glucocorticoids are part of blood sugar control and stress response. And then we mentioned earlier when somebody brought up rickets that vitamin D is necessary for the absorption of calcium and phosphate into blood. If we don't get enough vitamin D, then the rest of this process is not even possible. Vitamin C necessary for collagen, vitamin A activates osteoblasts, but back to calcitonin and parathyroid hormone. Calcitonin is released by your thyroid gland, and it's going to promote deposition, depositing, adding calcium to your bones. One thing to consider long term is there's two compartments. There's your blood and your bones. If calcium is not in your bones, it may be in your blood. If calcium is not in your blood, it may be in your bones. When we say that osteoclasts break down bones, what we mean is that they're breaking down that calcium and releasing it to the bloodstream, where it can then circulate. And when we say that osteoblasts help deposit bone, we're saying that they take calcium from the bloodstream and deposit it into bone. So when we say calcitonin promotes deposition into bone, in part it does so by inhibiting osteoclasts. It's also going to encourage osteoblasts. Parathyroid hormone is released by the parathyroid gland, and that's going to increase blood calcium levels by encouraging bone reabsorption by osteoclasts. So the Cookie Monster goes in and it breaks down that calcium in the bone and it releases it into the bloodstream. As we go forward in anatomy and physiology, what we'll eventually see is a number of different cells and mechanisms that require calcium to work. So your neurons are going to require calcium to work. Your muscle cells are going to require calcium to work. And they're far from the only ones that require calcium, but they're the ones we're going to focus on. So it makes sense if you have inadequate calcium intake from your diet, that we may go to your bones to supply your neurons and your muscles. Your neurons and your muscles firing in the immediate term is more important than your bones having a lot of structural integrity. We will always prioritize muscles and neurons if you have low calcium. Does that make sense?
Yeah. When would it show, like, roughly, like, an average of an age when you would see you really, all throughout your life, have used up your calcium?
Osteoporosis. So the question was, when would it show up that you've used up all of your calcium? And the answer for that is whenever you develop osteoporosis. Yeah. That's exactly the concept that we're getting to with that. Yep. Thanks for that segue. That's a good one. All right. If you use weight-bearing exercise throughout your life, you will be putting a healthy amount of stress on your bones, and you will always be encouraging your osteoblasts to deposit calcium into your bones. Your body will say, this is high priority. I need to have structural integrity because I am being used. Obviously, it's not conscientious like that, but that is how we evolved. We evolved to put priority on things that are being used. So this is why more and more health sciences are promoting weight-bearing exercises, especially for women. Because of our estrogen, because of childbirth. Childbirth uses a lot of calcium. We give a lot of our calcium to our infants. Because of our sex differences, we are much more likely to develop osteoporosis. And as such, we need to be doing weight-bearing exercise. More and more health, physical educators, personal trainers are being trained to say women need to be doing weight-bearing exercise. If we're doing marathon running, that's kind of the opposite. So when you're running a marathon, you're using your muscles, you're using your nerves firing onto muscles, you're using calcium when you run a marathon. And if you don't nutritionally replace that calcium, you leached a bunch from your skeleton and you didn't replace it. So a marathon runner is actually going to end up more likely to develop osteoporosis if they were not good about nutrition and also doing weight-bearing exercise. So women who lose weight by becoming cardio zombies, oh, I'm just going to, do 30 minutes on the treadmill every day, or an hour on the treadmill every day, or an hour and a half on the treadmill every day. That is not the kind of weight-bearing exercise that is going to encourage calcium deposition. That is going to use calcium for other things. So if you're working out like that, you need to be very careful with your nutrition, and you need to be doing weight-bearing exercise. And that's true for every person in this room, and it's true for every patient you're ever going to have. And a lot of women don't really like doing weight-bearing exercises, right? Why? Does anybody know why? Does anybody in here? Has anybody in here? Yeah, women think they're going to get buff, but it's not true. On average, women have, I can't remember the exact number, it's just much more difficult for women to put on the same kind of muscle mass that typically men are capable of. It's just biological sex differences that do pan out with the statistics. And again, it's biological sex differences. There are averages, there is individual variation. But by and large, women do not get super bulky. I do a lot of weight-bearing exercises. I'm bulky underneath my layers of squish, and I'm comfortable with it. But I'm strong as heck, so I'm happy about it. And it's never too late to start weight-bearing exercises, even when you've developed osteoporosis. With proper monitoring and proper guidance, the elderly population can start, lifting some light weights to help partially reverse, probably not totally reverse osteoporosis. Questions about that? So I encourage everybody to start lifting weights. Fracture repair, just 4 steps, pretty easy. First thing that happens when you break a bone is a hematoma forms. It's a fracture hematoma. A hematoma, again, is a collection of blood cells, basically. And then that forms there. It solidifies a little bit. At this point, it's definitely not weight-bearing. Gradually, a fibrocartilaginous callus develops. And we know from before that you can put some weight on fibrocartilage, right? You have fibrocartilaginous rings in your vertebral column, pubic symphysis. So this is developed a little bit for some weight bearing. Gradually, that fibrocartilage will be replaced by a bony callus. So it's still not the right structure. We still don't have those osteons that are formed in the direction of pressure of our weight. Right, I mentioned earlier, here's my femur, the direction of pressure is going to be mostly in this direction. In order for this to be fully functional, we need those osteons arranged in that direction, right? So over time, the bone will remodel, and those osteons will gradually be replaced, and that organization will come back, as long as you did put an appropriate amount of weight on it. Has anybody ever broken a leg and there's a certain time frame where they say you do need to start putting weight on it, even though it's a little bit painful, right? You do need to start using it, because that's how those cells know which direction to lay new bone in. If you don't put weight on it, if you do not use it adequately, those osteons will have random orientations that are not going to respond well to the pressures put on them. So that's really all you need to know there. Fracture hematoma, fibrocartilaginous callus, bony callus, remodeling. Yes?
Is the myth or statement true that after you break a bone it's stronger?
So you'll see here at the remodeling image, it never quite smooths down to the thickness it was before. So yeah, it actually does become stronger there. There's good things and bad things about this. It's not even off topic. I think this is a good, interesting topic to talk about. Your bones actually evolved some thinner spots that break more easily than others. And these spots tend to be farther away from really major blood vessels or really major clusters of nerves. So that's actually a good thing. So if you fall on your outstretched hand, you're probably going to fracture your wrist right about there at your, let's see, that's your radius. And that's going to be relatively safe in terms of nerves, arteries, and veins in that area. But then that's going to remodel and it's going to be thicker there. So if you fall on that wrist again, let's say you're a skateboarder and you're doing this all the time like an idiot, then the next time you fracture it, it may be closer to something vital and something that's going to leave you with nerve damage or something like that. Oh, types of bone fractures, always a super fun graph to look at. We like that, don't we? There's not a ton that you need to know about our types of bone fractures. Complete versus incomplete, open versus closed is generally what I focus on. Ultimately, you'll want to know about Colles, comminuted, compound, oblique, green stick. Who knows about green stick fractures? What's a green stick fracture? It's kind of exactly what it sounds like if you want to use some intuition. What happens when you break a green stick? Yeah, they'll still be together. It's only going to be a partial break. And you kind of get some splintering along one edge of it, right? So that's a green stick fracture. It's kind of small on my picture up here, but it should be relatively large up there.
Isn't that dangerous?
It has its own dangers. It's more likely to happen in immature young bone. So this is going to be more of a childhood injury than an adulthood injury.
What does the first one say?
This one, Colles. Colles. So Colles, fracture of the distal end of the radius, produces a dinner fork deformity. So each of these has its own significance. I'm not going to test you on every single one of them. All right, I'm not going to lecture the chapter that does just the axial skeleton, because that's basically just a list. I might do a little mini lecture later about talking about, let's see what's on there, gender differences between men and women in the skull. I think there's something else in there, but otherwise it's a list of bony features, and I'm not going to lecture that because it'll just be me saying words for an entire hour, and it will wash over you, and you won't catch any of it. That would be entirely useless. I've tried it that way, it doesn't work. What is useful for me to actually lecture on is the linguistics. The names and the naming conventions that we use to actually name bony markings in general. Because if you can get these, then the words on that gigantic list of bony features that you need to learn will make sense. They translate. So this is fairly well organized. They're going to have articulating surfaces. They're going to have depressions or hollows. They're going to have things that are projections or roughened portions that'll be attachment sites for tendons and ligaments. And then you're going to have openings and spaces, or holes, basically, holes in your bones. You're going to see some condyles, and a condyle is going to be a sticky outy bit. I'm going to use the word sticky outy bit a lot, which is a ridiculous word, but it's very, very accurate. It's a bit that sticks out. Sticky outy bit. Condyle is going to be one type of sticky outy bit that is smooth. And this screencasting this is going to be very difficult. I'm going to go grab Bob real quick so that I can show you some condyles. Okay, Bob is really hard to move across the floor, so this is going to look ridiculous. We need a better Bob. That's about as smooth and elegant as that gets. So here is an example of a condyle. It sticks out. You can kind of grab it. It's a rounded, smooth surface. That's a condyle. If you see a sticking out, rounded, smooth surface, it might be a condyle. This word is facet. I used to pronounce it facet because it is very similar in nature to the facets that you might get on a gemstone, like a diamond. You guys know what facets are, or facets are on a diamond. It's that smooth face that's like going to sparkle in the light. So it's not separated out here, but you have your facets. You have these flat surfaces on your vertebrae that articulate with the next vertebra up. Those are facets. And I don't care which way you pronounce it, facet, facet. I think they're both accurate. In grad school, everybody pronounced it facet, so I got that habit. A head is going to be similar to a condyle. So you have your head of your femur. It sticks out and it's rounded and it's smooth. You're going to see heads at, let's see, this is the proximal epiphysis of the femur. That's the head of the femur. This is the proximal epiphysis of the humerus, and that's the head of the humerus. So they look like heads. They're big and smooth, so call them heads. Trochlea. We're not going to see too many trochleas. This is a trochlea. Again, these are articulating surfaces. So you have this big, knobby, rounded bit. Everything, this fashion is getting a little out of hand. From here to here, this is all a trochlea. So that articulation at your elbow, it all articulates across that trochlea. I think that might be the only trochlea you have to work with. Now we get to some depressions. Alveoli, when you think of alveoli, I just want you to think of teeth. The alveoli are your depressions for your teeth. That's pretty much the only place you'll see those. You'll see a few fossae. A fossa is a broad depression. So let's see. This is the infraspinous fossa. So it's a little bit concave. So there's this concavity. This is the supraspinous fossa. It's a concavity and it's smooth. This is not an articulating surface. This is a depression. This is some muscles are going to lie here, but there's no other like bone articulating with it. Sulcus is going to be a narrow groove. Let's see if I can think of a sulcus real quick. I mean, there's a bunch of them, but let's see. Does anybody think of a sulcus real quick? You have a bunch of them. I don't know why. I always have a brain fart for one of these. Sulcus. You'll have a variety of narrow grooves in between some spaces, and those will all be called sulci. I'll find a better one. Okay, crest. We're into projections now. A crest is going to be a narrow bit that sticks out. So this is narrow and it sticks out. This is the iliac crest. An epicondyle, we did condyles earlier. Those are the knobby bits that are rounded and articulating. An epicondyle is going to be immediately superior to a condyle. That's really it. So condyle, epicondyle, condyle, epicondyle. A line. Let's see, linea aspera. You have some just ridges on the diaphyses of long bones that you can usually feel with your finger. It may or may not be very obvious or visible in a two-dimensional image, but you can feel it and prove it to yourself that there's a line there. So this is linea aspera. The first one that comes to mind for a line. A process is going to be a heck of a lot like a condyle. Yeah. Let's see. Tubercles. Radial, tubercle, still tubercle. Process, condylar, I think this is a process right up here. Condyloid process. It just sticks up. It's like a little mini spine or crest, if you will. Okay, spine, trochanters, tubercles, and tuberosities. Tuber has the same word root for potato. So somebody looked at some big rough patches and thought, that looks kind of like a potato. And somebody said, well, that looks like a little potato. And that looks like a bigger potato. So they called little potatoes tubercles, and they called the bigger potatoes tuberosities. Has anybody heard the word tuber for potato before? No, I'm alone in that. I think botany term, maybe Latin. Trochanter is going to be the biggest potato, but you've only got 2 on each side. Greater trochanter, lesser trochanter. Greater trochanter, lesser trochanter. That's it. They're really big, they're really knobby. They're going to be really good attachment sites. All your tubercles, tuberosities, and trochanters are really strong attachment sites for a variety of muscles, tendons, ligaments. So they're going to be really close to very, very important joints. That's where you're going to find those. As for holes, mostly we're going to use the word foramen. Plural is foramina. If it's a hole, your first guess is going to be foramen. If it's a slightly bigger hole, you might call it a canal. If it's a hole that is elongated, you might call it a fissure. And if it's a space and a cavity inside one of your cranial bones or your facial bones right here, they'll call it a sinus. And that's it. That's it for bony marking terminology in general. We did normal versus osteoporosis. If over the course of your lifetime you remove more calcium from your bones than you deposit, determined partially by your hormones, how many children you gave birth to, if any, and whether or not you had weight-bearing exercise or certain hormonal disorders, such as problems with your calcitonin or parathyroid hormone, then you could end up with osteoporosis. And that's about it. Okay, questions before I turn off the recording? Turning off